Imagine standing on a pier as a steel monster, weighing well over 100,000 tons, stretching longer than 3 football fields end to end, and carrying thousands of steel shipping containers, glides silently straight toward you. It towers over the dock like a moving 15-story skyscraper. Now, imagine the captain suddenly panicking and trying to hit the brakes. Here's the terrifying truth. There are no brakes. There are no brake pads clamping down on massive wheels, no rubber tires gripping solid asphalt, and no emergency foot pedal to floor when the concrete pier gets dangerously close. Yet every single day, these floating leviathans pull into crowded harbors, navigate narrow channels, pass beneath low bridges, and park beside solid concrete walls with just a few feet to spare. How is that even possible? The real secret isn't how these ships stop at the dock. It's that the stopping process began miles out at sea, long before anyone on shore even saw the ship on the horizon. And if the crew makes just one wrong mathematical calculation, that quiet parking job transforms into a multi-million-dollar demolition derby. To understand how a giant ship stops, you first have to understand why the ocean is a driver's worst nightmare. When you step on the brakes in your car, solid ground takes all that kinetic energy and burns it off through immediate tire friction. But a ship floats on water, and fluid gives you almost zero stopping friction. And here's where the physics get genuinely terrifying. If a captain simply shuts off a fully loaded cargo ship's engines while cruising, the ship doesn't freeze in place. It keeps coasting forward through the water for miles and miles. Even at what looks like a total crawl, say 3 or 4 knots, that tiny speed multiplied by a mass of 100 million kilograms creates a staggering amount of forward momentum. Kinetic energy scales exponentially with speed, but when the mass is that immense, even a fraction of a knot holds enough force to crush a concrete pier like a soda can. That energy has to be systematically bled off into the ocean. How far the ship drifts depends on its underwater hull shape, how deeply it's floating in the water, local currents, and even the depth of the seafloor beneath it. A deep-draft supertanker scraping close to the harbor floor will coast completely differently from a lighter, tall-sided container ship. This is why a captain never waits until they can see the dock before thinking about slowing down. The maneuver is already well underway while they're still in deep, open water. Long before the harbor even appears on the horizon, the bridge team is running complex calculations. They're analyzing tide charts, predicting wind vectors, mapping underwater topography, and calculating traffic density in the approach channel. Why all the extreme prep work? Because of a dangerous phenomenon known as the channel trap. Most major shipping ports require massive vessels to travel through strict, narrow underwater corridors. If the ship strays even a few yards outside that invisible underwater lane, it will run aground in shallow water, gouging its hull or grounding the ship entirely. That means if something goes wrong during the approach, the captain cannot simply turn the wheel and steer out of harm's way. They are trapped. They have to shed all that velocity while locked inside a narrow, unforgiving corridor of deep water. This is the exact moment a specialized harbor pilot boards the vessel. Delivered by a small boat or dropped onto the deck by helicopter, the harbor pilot is a master local navigator who knows every hidden current, bridge clearance, and shallow mudbank in that specific harbor. While the ship's captain remains legally in ultimate command, the local pilot takes over tactical navigation. Together, the bridge team executes a meticulously timed sequence of moves. On a ship of this scale, a command given to the engine room or helm right now won't produce a noticeable change in the ship's path for tens of seconds or even several minutes. Instant gratification simply does not exist at sea. So, if you can't coast to a sudden stop and you can't steer out of the channel, how do you actually shed that relentless momentum? Your primary tool is the main engine and the massive propeller at the stern. During normal ocean travel, the main diesel engine turns the propeller, pushing millions of gallons of water backward to drive the hull forward. To slow down, the bridge team starts by dialing back the engine power, letting simple water drag begin the long process of bleeding off speed. But if they need stronger deceleration, they have to push force in the opposite direction, a maneuver known as going astern. But you can't just throw a 100,000 horsepower marine engine into reverse like you're shifting a pickup truck into backup mode. Attempting that kind of violent shift while moving at speed would instantly shatter the drive shaft, blow out the engine's compressed air starting system, or tear the propeller blades off entirely. On traditional ships with fixed-pitch propellers, the crew must first slow the massive engine down, cut fuel, bring the multi-ton steel crankshaft to a complete dead stop, and then use compressed air to physically restart the entire engine in the reverse direction. Even once the propeller starts spinning backward, churning water forward toward the bow, the ship's massive momentum keeps dragging the hull forward through the sea. The reverse thrust collides with the oncoming water, creating a wild, turbulent, chaotic wash around the stern and rudder. The reverse thrust steadily fights the forward inertia, but the vessel still requires massive amounts of time and miles of open water to come to a complete standstill. Some modern vessels utilize controllable pitch propellers instead. On these ships, the engine shaft keeps spinning in the exact same direction at a constant speed, but the individual mechanical blades on the propeller hub rotate their angle. By twisting the blades, the system can instantly reduce forward thrust, flatten out to zero thrust, or twist fully to direct thrust forward to pull the ship backward. This provides the bridge team with far more immediate and precise control, making it ideal for cruise ships and ferries that dock multiple times a day. Yet, even with blade pitch control, you cannot instantly erase 100,000 tons of moving steel. Changing blade angles alters the force you apply, but it does not erase the laws of physics. And that brings us to the rudder paradox, one of the single most dangerous mechanical challenges in seamanship. A ship's rudder does not have its own motor to turn the boat. It works like an airplane wing placed vertically in the water, relying on fluid actively flowing past its surface to generate hydrodynamic lift and pivot the stern. At high cruising speeds, immense volumes of water sweep past the rudder, giving the captain sharp, responsive steering control. The paradox: as the ship slows down to safe harbor speeds, the water flowing past the rudder drops dramatically. The rudder becomes sluggish, squishy, and eventually almost completely useless. Right when the ship gets close to concrete piers, shallow banks, and multi-million-dollar bridges, the exact moment when precise steering is most critical, the vessel loses its ability to steer. To combat this, pilots use tactical bursts of engine power to blast a jet of water directly over the face of the rudder, a technique known as kick of the engine or propeller wash. This gives the rudder temporary steering authority without adding too much overall forward speed to the hull. To make matters worse, every giant ship possesses its own quirky, erratic personality. When you reverse the engines, the rotation of the propeller blades creates a sideways torque effect known as transverse thrust, or propeller walk. On many ships, going astern forces the stern to walk sideways to port, unexpectedly turning the bow to starboard regardless of what the rudder is doing. Add a 20-knot crosswind into the mix, and a massive container vessel stacked high with colorful boxes acts like a giant 1,000-foot-long steel sail. A strong gust hitting that high surface area will slide the entire multi-thousand-ton vessel sideways off course like a bar of soap across a wet floor. This is where the unsung heroes of the maritime world step in: tugboats. Looking at a tugboat floating next to a mega container ship looks like an ant trying to muscle an elephant. But these compact harbor craft are engineering marvels, packed with thousands of horsepower and equipped with omnidirectional propulsion drives that allow them to push or pull with immense force in any direction imaginable. Tugboats connect to the massive ship using thick, high-strength synthetic lines, or position themselves directly against heavily padded sections of the ship's hull using massive rubber fenders. Depending on the pilot's docking plan, one tugboat might manage the bow while another controls the stern. They don't attempt to overpower the cargo ship's momentum all at once through brute force. Instead, by applying steady, calculated vector forces over a prolonged period, tugboats slowly nudge, hold, and pivot the Leviathan, counteracting wind drift and guiding the vessel into the slip with extreme delicate precision. Tugboats are especially crucial when turning a giant ship in a confined harbor basin. under its own power, a 1,000-foot ship might require a turning radius over a mile wide. But inside a designated turning basin, tugs can push the bow in one direction while pulling the stern in the opposite direction, spinning the giant vessel virtually on a dime. Modern ships often supplement tugboats with their own built-in maneuvering systems, bow and stern thrusters. These are secondary propellers mounted horizontally inside underwater tunnels that run straight through the hull from left to right near the front and rear of the vessel. Instead of pushing the ship forward or backward, thrusters push water sideways, driving the bow or stern laterally. Cruise ships, which must berth in tight tourist ports daily, carry multiple powerful tunnel thrusters, allowing them to slide sideways into a docking slip without needing tugboat assistance in calm weather. Other specialized vessels utilize azimuth thrusters, external propulsion pods hanging beneath the hull that can rotate 360 degrees, directing full thrust toward any point on the compass. When hooked up to satellite navigation systems and onboard computers, these dynamic positioning systems can hold a vessel rock steady over a precise spot on the ocean floor, completely counteracting wind, waves, and ocean currents automatically. So why don't all massive cargo ships just rely on built-in tunnel thrusters and throw away the tugboat budget? Because tunnel thrusters rapidly lose their effectiveness if the ship is moving forward through the water at anything more than a slow crawl. The rushing water flowing along the outside of the hull disrupts the sideways jet exiting the tunnel, destroying its push force. Furthermore, against heavy ocean currents or gale force winds, built-in thrusters simply lack the sheer raw tonnage of push force provided by multiple high-powered harbor tugs. Port authorities often mandate tug escorts regardless, serving as a critical safety net if a ship's main engine or electrical generators suffer a sudden blackout inside the harbor. Speaking of catastrophic failures, what happens when everything goes completely wrong? Can't the crew simply drop the heavy steel anchors as an emergency handbrake? Hollywood movies have lied to you for decades. Dropping an anchor on a fast-moving cargo ship will not cause it to slide and stop like a stunt car. If a 100,000-ton vessel drops anchor while traveling at high speed, the anchor will not grab the seafloor and snap the ship to a standstill. Instead, the anchor will drag violently across the seabed like a skipping stone. If it does manage to dig in and hook solid rock at high speed, the mechanical tension will instantly rip the windlass machinery right out of the deck or snap the multi-ton forged iron chain links like twigs, sending lethal whipping metal across the forecastle. In a genuine emergency, dropping an anchor into the seabed can be used to drag the bow around or gradually shed residual speed, but only if the water depth is right, the seafloor provides soft mud or sand, and the ship has already been slowed down significantly. Anchors are a tool of positional holding and gradual emergency drag, not an instantaneous stopping pedal. By the time the giant ship finally enters the immediate berth area, its speed has been systematically scrubbed down to mere fractions of a single knot, moving considerably slower than a walking turtle. The bridge team continuously monitors laser distance sensors, high-precision GPS, marine radar, and real-time radio reports from deck officers standing directly at the bow and stern visual edges. The primary objective is almost never to drive the ship's bow straight toward the quay, but rather to bring the entire length of the vessel perfectly parallel to the dock. Giant shock-absorbing rubber fenders mounted along the concrete wall compress under the ship's massive weight, absorbing the tiny bit of residual kinetic energy left in the hull without cracking the ship's steel plates or shattering the dock's foundation. Once the ship is gently resting against the fenders, heavy synthetic mooring lines, including headlines, stern lines, breast lines, and spring lines, are pulled to shore by small workboats and thrown over solid steel bollards on the pier. Powerful automated winches mounted on the ship's deck strain to adjust line tension, physically pulling the vessel into its final alignment and locking the multi-ton giant in place. When you stand on the shoreline and watch a massive ocean-going cargo ship resting peacefully beside a container terminal, it looks simple, quiet, and effortless, as if the captain simply pulled up and put the transmission in park. But what you are actually witnessing is the grand finale of a miles-long, highly calculated physics experiment involving fluid dynamics, mechanical force, local knowledge, and absolute patience. There was no sudden panic, no single lever pulled, no brake pedal slammed, and no magic button pressed. The ship didn't come to a halt because it finally reached the concrete dock. It reached the dock safely because it started stopping miles out at sea.